So here's another simulation exercise. In our system, we have a tank that we can control the tank level. But now we are going to look a little, this is called continuous control. And basically we are going to use a PID controller. So just look a little on the background here, continuous control, the controller PLC interconnection and how to simulate this. We should do simulation, PLC hardwiring. The CPU, we have a controller. We are not going to write this controller in our template project. There is an FB called Control Analog Absolute, which is a controller with the basic functionality, the bare necessity that you need. So automatic and manual mode and so on. Gain and integration time and differentiation time, and there's a dead banner in it too, and and so on. So you can do a little bit an automatic mode, a manual mode, set pointers and in our parameter, and the feed forward value or this Y0 value, the bias is here. But how to wire this, and here I just put some, here's a transducer, lever transducer from Endres and Hauser, mounted at the bottom because it's measuring pressure, don't mount it here. This is just out of the manual of this level transmitter. And okay, so that's the level, and here is how to wire it, 4 till 20 milliamps output on this interface here. So here's the cabling, and then we wire it as a 2-wire 24 volts out here, and then we have 4 to 20 milliamps back through this resistor and then to our ADC, and it ends up in a register on AM module and in the CPU on an input image here. So this memory input image is in the CPU, but just to save some space, I put it on the A module. But there's only a register on the A module. And also the controller has an output, 2 bytes, output image, and then to the AO module, and on the channel 40 milliamps out here. How to connect it, I think is ED, maybe E. 40 20 milliamps too. It seems to be here. It's 100. The resistance is greater than 100 ohm, so you don't fry your output. So we check that. And Rexroth, that's a component, produce valves, control valves. Okay, so this is what we call legacy hardware. Normally, a field bus normally used to connect PLC to the sensor, maybe not the sensor, but at least the actuator, if you have that. So this is kind of legacy hardwiring if you have to do it, and if you do, use 4 till 20 milliamps. So again, simulation, this is the memory in the CPU, this is just the CPU, and we do something here. We have a tank simulator, we have some input output scaling, so controller is working on this 0 to 27,648. We use the minimum to maximum value for analog measurements in a schematic, so it's a PID controller with some parameters, okay, and here is the controller again, right to the output image to the tank simulator, and here is, could be something like this, a tank is basically just an integrator. In our model, there's a little more to it than that, and this analog input output function that you could use just to interface this, so here, this tank simulator is working 0 to 20 cubic meters, the volume if that's what you would desire. And these function blocks here too, they are in this template project. So you can make yourself some kind of a tank simulator. There's a little more in that project. So the simulator we are using here in this template project has a little more functionality than this. And then again, there is this norm, the IEC 63131, PID controller according to PID controller. So input, your measurement, your control value, and there's more to external reference, that's set point external reference called tracking value. You can do fully open, fully closed. Feed forward value, this is bias value that you have, lock safeguarding, you can do it. Operator state interface and so on. If your control valve here is fully open, fully closed, if it's safeguarding blocked and deviation warning, which means that your error is too high or something, and you have a warning high and low too, that if the value you are controlling here, if this was a tank level, is a level too high or too low, So that's functionality, this control analog, control analog, it's called continuous control. And there's a lot of parameters that you can manipulate. There's somewhere here you should have the PID, the KP, TI, and TD parameters too. And here are some initial values that you should have. So it's configured as a pure P controller, it looks like here, as a starter. But there's more to it. So if you want to program a controller yourself that does something, maybe you should look into the norm, because this one tells you basically more about this. This is just a snag out of a little information. Yeah, and this too shall not be used in downstream logic, so you can't use this deviation warning to do some actions downstream, and not these either. So, okay, so these are not action alarms, they're just warnings for HMI system, alarms and faults and so on, and the status and output. So you can't use it for some logic that should do anything. So, okay, so this was an introduction to, let's say, continuous control. What we looked at was hardwiring to a PLC, and then we looked at simulation using an integrator and some input-output scaling. Those are function blocks that is in this template project that we are using. And then we looked at a full-fledged PID controller with 30 years of experience built into it. That would work pretty well with a lot of processes. It does, because that's been tested. I've even tested it myself, that a function like this is adequate for single loop control too. But you can connect it to other controllers and do cascade control and so on, and you can have logic around it, do quite a few things. You have an external set, but you can track something if you want to switch it off. So there's a lot of functionality. This standard function that we have here.